Hello, students. Had a couple questions come in about isosceles trapezoids. And so I wanted to go ahead and deal with those. They were really asking about these three pieces here. So we might as well. Notice the definition. Isosceles trapezoid is a trapezoid, which again, you got to go back up and say, what's a trapezoid? Quadrilateral with at least one pair of parallel sides. If it has at least one pair of parallel sides, then it has a pair of congruent base angles. And they're listed here. So that's the definition. Now, again, what we're trying to show is if something meets that definition, can we guarantee that each pair of base angles is congruent? Can we guarantee that each pair of opposite sides is congruent? So again, that's kind of the idea. And then lastly, if a trapezoid has congruent diagonals, then it is isosceles. Okay, this one I'll put a little asterisk by this because this one is a little bit trickier, and you could have another one, I guess, not for this exam, but you could have someone say, "Well, what if I know the sides? It's a trapezoid, and I know the opposite sides are congruent. Does that mean that it has to be an isosceles trapezoid? Which means would it guarantee me that the the rest of the pieces have to be congruent. These base angles have to be congruent." Well, let's start with the first one. So if we know it's an isosceles trapezoid, can we guarantee that each pair is congruent? So again, we know one pair is congruent, so I'll label those as X and X. And let me see here, maybe I can zoom in a little bit, make that a little bit bigger. There we go. Okay, let's do that. All right, so what does that mean? So I have X and X. The other two base angles are, we'll just call them Y and Z because I don't know if they're the same. But we do have parallel lines. Parallel lines from chapter 11, the angles on the same side of the transversal add up to 180 degrees. So X plus Y, that's 180 degrees. And X plus Z, that's 180 degrees too. Okay, well, that's fantastic. They both have an X. Let's bring it over to the other side. So what we're saying here is that Y is equal to 180 degrees minus X. Z is equal to 180 degrees minus X. These are the same quantities by the transitive property. Y is equal to Z. And so that shows that the other base angles have to be congruent. Okay. Didn't really use too much about trapezoids. It was really just about parallel lines and something we know from back in chapter 11. Next one, each pair of opposite sides has to be congruent. Okay. For this one, let me go ahead and get a little bit of white space right above me because I want to show you something kind of a kind of a cool way to think about this. At least this is how I kind of think about this one. So I want to think about this. I want to extend the line up. Okay. And I'm going to do that from both sides. Okay. Now let's talk about what we know. We know that these lines are parallel, BC and AD. Okay, so this line here is parallel to this line here. We know the base angles are congruent, and because they're parallel, we know corresponding angles are also congruent, which makes, let's see, maybe I'll make an E up here, which makes BCE, this triangle sitting up on top now, because the base angles are congruent, this has to be an isosceles triangle. So I'll call this piece BE, I'll call that X, and over here EC, I'll call that X because they have to be the same. And likewise, look at this big side. And again, on this one, look at this big side down here. EA and ED, that would form a big triangle, almost like you're ignoring BC, just kind of cover it up with your finger for just a moment. But it also forms an isosceles triangle because the base angles are congruent. That means the long piece here, which I'll call Y, has to be the same as the long piece here, Y. So the missing piece, if I was to call it, I don't know, M on this side and N on this side, then what we could tell is the long side, which is y, is equal to what? M plus x. And on the other side, y is equal to n plus x, which means that y minus x is m, but also y minus x is n. And by, once again, the transitive property, m has to equal n. And if m equals n, then the opposite sides are congruent. All right. Last one, if it has congruent diagonals, it is isosceles. All right, so now um, this one, the reason I put a little asterisk by it is it's a little bit different than most of the other ones, and here's why. Here's why. Here's what we're gonna do. I'm gonna get a little bit of, maybe I'll just put white space over what they already have, so I don't have to redraw everything. We'll get a little bit of white space over here. Okay. And I'm gonna draw in the diagonals. Oh, that looked perfect. Okay, let me go to the straight line tool because it's a little bit later at night. There we go. Oh yeah, fantastic. That looks great, Scott. How do you draw them so straight? I draw these in. What do we know? We know that this is a trapezoid. So we know BC is parallel to AD. And we know that BD has to be congruent to AC. All right. Well, let's take a look here. Here's what I'm going to do. Here's what I'm going to do. We're going to do a construction that we've done before. See this line BD right here? And this point C? I'm going to make a parallel line to BD, and it's going to go through C. And like that. So I have parallel lines. And then I can extend AD, just like with your straight edge, just extend the line to wherever it hits. And now I'm going to go ahead and draw a shape here so you can hopefully see it if you're following along at home. And let's see here, highlighter shape. I want you to look at this triangle, this great big triangle right here, okay? Now it's A, C, and then I guess I'll put point E out here, okay? ACE. All right. Now here's the fun part. This side length right here is one of the diagonals. The other length right here, which is CE, is the exact same length as BD. It's like, because I did parallel, I just shifted it over. Okay. So I've now created a parallelogram, and parallelograms have opposite sides that are congruent. So CE is the same as BD, which means it's the same as AC. All of that is cool and super fun. But here's what I want to get at. Oops, I erased my line. Here's what I want to get at with this. What it means is, it means this length is the same as that length. Now that means we have what? It means we have an isosceles triangle. When we say isosceles trapezoid, big hint, be looking for isosceles triangles as you go. So that means this angle right here has to be the same as this angle right there. Okay. And I'll draw back in this other diagonal we had, which was equal. And notice BD, we created it to be parallel to CD. So BD is parallel to CE. And that means corresponding angles are congruent. So this angle right here has to match the angle right there because of the two parallel lines. The transversal now is being the line AD, or AE if you prefer. Okay. So that's kind of cool. Now I'm going to go ahead and I'm going to kind of erase parts of those just so we can focus on the pieces now that we have over here. Let's take a look at what we have. I have congruent diagonals. I have two angles that I've now proven have to be exactly the same. And this length down here at the bottom is congruent to itself. And while it's a little bit hard to see, maybe I'll sketch it over here so we can really kind of see the two triangles that I'm looking at. One triangle looks like this one, and it's CAD. And notice the piece I have I have this length right here. I have this angle down here, and then I have this length at the bottom. Compare that with, if I repeat this, and I go from B down to C, or down to D, and then back over to A, I make a triangle here, and let's check to see if they are indeed congruent. I have this length, which is a diagonal, which is congruent, and again, that's because it was given to us. They told us it had congruent diagonals. The angle in the corner is the same, and this piece across the bottom is AD, which is congruent to itself. And that means I have congruent triangles. If you have congruent triangles, you get corresponding pieces that have to be exactly the same. Phew. Now, if those sides are the same, right? Now our goal again was to try to get the, I guess we could say sides are the same if we needed that. If we needed angles to be the same, then I would have come here. Let me just make this a little bit bigger and say, then this angle is corresponding to this angle, so therefore they must be congruent. And that would be the definition then of an isosceles trapezoid. It's a trapezoid with a pair of congruent base angles. Okay. It is tempting. I'm not gonna lie. There's a temptation here for me to kind of think of the diagonal coming here, the diagonal coming here, and think of using two different triangles. One triangle up here that looks like this one, and one triangle up here that looks like this one. And the reason I kind of like this is I have a great big angle here, okay, and a great big angle here. I have a side that is congruent because it's congruent to itself, and then I have diagonals that are congruent, right? And again, this would be like an ASS or an SSA type of idea if I knew these. Like if I knew this was an isosceles trapezoid, then a pair of congruent base angles, one of them has to be acute and the other has to be obtuse, or they're both right angles. And if they're both right angles, then you have more than an isosceles trapezoid, right? Okay, now you have a rectangle. Okay. So anyway, that's kind of the idea with an isosceles trapezoid. You get these other pieces, and you can look at this as ASS, SSA, but because the angle is large enough, because it's not an acute angle, there would be exactly one option for that. So again, this kind of would be okay. I'm not going to get into that because it, again, seems a little sketchy at times for me to be saying if the angle's big enough, then ASS would work. So it's like big ASS or big SSA, big angle, but again, doesn't really do too much for us. Just understanding ASS or SSA is not enough by itself. We need more information. I guess we should just kind of put it that way, and we'd be okay. So there you go. Those are the pieces with isosceles trapezoids. Again, you could always say, here's a shape. BC is parallel to AD, even if you don't know the name isosceles trapezoid, right? And, those are parallel, and the sides over here are congruent to each other. Could you prove that those base angles have to be congruent? And hopefully, yes. That one might even be a little bit easier because you could draw a diagonal in here, right? And then this triangle side, side, side would be identical to, drum roll, put another diagonal in here, go down here, and you'd have again side, side, side. Two triangles are congruent, and that means the corresponding parts have to be congruent, and you get the congruent angles, and therefore the definition. So you can't go any of these directions on the test. I'll tell you exactly what kind of shape it is, I promise. I'll tell you this is a parallelogram, or I'll just tell you the two sides are parallel. Prove opposite sides are congruent. Prove opposite angles are congruent. All right, there we go. Hope that helps. Get you on the right track. If you have other questions, let me know. And again, I can jump in Zoom, meet up with you, or I think we still have time. Meet up on campus if you prefer that. And hopefully you're getting yourself ready for this test. All right, off you go.